Okay, so last week when I started off with this particular chapter in my screen flow, I made an error and wasn't able to save it. So I'm rebroadcasting this so that you'll have it for your YouTube videos that you can go back to and look at your leisure. So today we're going to talk about alcohols and ethers. And so as you'll recall, we went through some previous stuff from chapter 10, which was the free radical chapter, and we talked about radical stability. And the question was, which radical is the most stable? And after you look at these, you recognize that you have a primary radical for A, you have a tertiary radical for B, you have an allylic radical for C, which is also secondary, and you have a tertiary allylic radical for D. And so we know that radical stability follows carbocation stability, so tertiary should be better than secondary, should be better than primary. And so if we think about that, the choices that we should be pondering are B and D. And D is the correct answer because not only is it tertiary, but it's allylic. So it has the stabilization due to its tertiary, being a tertiary carbon atom or carbon-centered radical, but also the resonance delocalization that would result from it being allylic. We also talked about this question: what is the expected stereochemistry of the organic product from this reaction? So again, starting from the R isomer of that hydrocarbon, doing free radical chlorination, we get the alkyl chloride shown, plus a molecule of HCl. Again, it starts with the R isomer. And so our potential answers are S, isomer only, R isomer only, equal amounts of RNS or unequal amounts of RNS. And it turns out that the answer here, of course, is C because in this particular free radical process, remember one of the propagation steps is going to be where chlorine radical abstracts the hydrogen from the R isomer, giving the benzylic tertiary radical that forms. And that tertiary radical is planar, or pretty close to planar anyway. And the odds of that radical reacting with chlorine from the top face and the bottom face are 50-50. And so you would end up with an equal mixture of RNS uh, enantiomers in your product. We also talked about this particular reaction. If you look at it, you'll notice that this is a free radical bromination. And if you'll recall back from chapter 10, you'll recall that free radical chlorination actually gives a variety of products, but bromination is usually pretty selective for the most reactive hydrogen. And in this particular case, we recognize that we have a hydrocarbon that has primary, secondary, and tertiary hydrogens. And so the tertiary hydrogens are the most reactive towards free radical bromination. It's very, very selective, and so the answer here is D. We talked about this one as well. Which of the following would be the reactive intermediate when 1-octene is treated with hydrogen bromide in the presence of peroxides? So we've got 1-octene and HBr. That's a free radical process when we have peroxides around, and so the answer here is B because it's the bromine radical that adds to the terminal end of the alkene to give the most stable radical intermediate, B. And so you should have eliminated A and C right off the bat because bromine's certainly not involved at all in the intermediate that you see. And D is the result of the bromine radical attacking the most substituted carbon. And that gives a primary radical. And so we know that secondary radicals are more stable than primary radicals, and that's why B is the correct answer. So then we got to talking about alcohols in general. Of course, you'll recall that alcohols are OH. We can also have enols where the OH group is attached to an alkene. These are not alcohols per se. You'll recall back from 255 that enols can actually undergo enol keto which is not shown here, but they are their own functional group. They are not like a typical alcohol. They have different reactivity. And we can also have phenols where we have an aromatic ring attached to a hydroxyl group. And so if the arrow group, of course, is a benzene ring, we call those phenols. So some examples, of course, ethanol or ethyl alcohol, isopropanol or 2-propanol, and cyclopentanol. All of these are examples of the typical ROH type alcohols. We can also see that both the enol and the phenol have the OH group attached to an sp2 hybridized carbon atom from the alkene or the aromatic ring. And so you might predict, in fact, that these two subclasses of alcohol should have similar chemistry. But in fact, the phenol, being part of an aromatic ring, has additional chemistry associated with it as well. So we do not classify phenols as enols, even though it kind of looks similar. The chemistry is actually quite different. We'll learn more about phenols as we go along this semester in class. You'll recall that ethers are oxygen-containing species where the oxygen is bound through a sigma bond to two different R groups. Well, two R groups. The R groups can either be identical or different. The R groups can be alkyls, alkenols, alkynals, or aryls. Cannot be carbonyls. If they're carbonyls, then we have a different functional group called an anhydride, which has different reactivity. But nonetheless, if R and R prime are identical, we call that a symmetrical ether. If R and R prime are not the same, we call it an unsymmetrical or an asymmetrical ether. Okay, so here are some examples. You see the dimethyl ether there on the left, and then the ethyl vinyl ether there in the middle, and then you can see the aromatic ether on the right. And the last two are actually unsymmetrical ethers, whereas the first one is a symmetrical ether. So melting points and boiling points, physical properties. Remember that the melting and boiling points tend to increase as the hydrocarbon gets larger in these so-called straight chain alcohols. Branched alcohols will form a separate subgroup. In terms of the solubility, don't forget that rule of thumb, but a small alcohol, something like methanol, ethanol, or propanol, they're going to be completely soluble in water. After you get to about 3 or 4 carbons, you're going to see some solubility, but once you get beyond 5, you're going to see limited solubilities. So for example, again, methanol, ethanol, and propanol shown there on the left, completely soluble in water. The alcohols on the right, the butanol has about 8.3 grams per 100 milliliters of solution. That's fairly soluble. It's about 8.3% by weight volume percent. It's pretty close to that 5 carbon rule, but not quite, so it is still somewhat soluble. However, if you look at the nonanol, you can see that the solubility is actually quite low. And that's because that one OH group, which can form hydrogen bonds with water, just has too many carbons to overcome the benefits of forming hydrogen bonds. Alcohols, of course, can form hydrogen bonds with themselves, shown here. You can see that a molecule of methanol will actually interact with another molecule of methanol through a hydrogen bond. Actually, it'll form a pretty extensive network of hydrogen bonds. This single hydrogen bond that's being depicted is just an oversimplification of the actual process that's going on in solution. And so methanol actually has a fairly elevated boiling point compared to what you would expect for a molecule of similar size that can't form hydrogen bonds. And so hydrogen bonding is in fact influenced by the organic structure, and so primary alcohols can form really good hydrogen bonds. Secondary alcohols, they're okay, but not quite as good. And then tertiary alcohols, while they can form hydrogen bonds with themselves, there's just a lot of stuff around that carbon bearing the OH group, and you have that increase in steric hindrance that leads to diminished ability to hydrogen bond with itself. And so here's some more physical property data. You can see in terms of boiling point there at the top, you have butane versus ethyl methyl ether versus propanol. All of these molecules have very similar molecular weights, but you can see that the boiling points are quite different. For the pure hydrocarbon, we simply have a boiling point of 0 degrees because the only thing we have there is van der Waals interactions. Whereas with the ether, we still have the van der Waals interactions, but now we have dipole-dipole interactions as well, because oxygen, of course, being electronegative, creates polar bonds within the molecule. And you can see that the boiling point jumps up about 11 degrees. So quite substantial increase in boiling point simply by replacing a carbon atom in butane with an oxygen atom. And then looking at the isomer of that ether, we get to the propanol. You can see that the boiling point goes up quite dramatically, and that's because now do we not only have van der Waals and dipole-dipole, but we also have hydrogen bonding involved. And you can also see that the boiling point increases as the extent of the hydrogen bonding increases. Going back to that primary, secondary, and tertiary alcohol argument on the previous slide, you can see that the primary alcohol has considerably higher boiling point than the secondary and tertiary alcohol. So that seems to follow quite well. Some interesting alcohols. Of course, ethanol is one of the more common alcohols that people learn about. This is generated by the fermentation of a variety of things. If, however, we are fermenting grapes, we make wine, which contains ethanol. If we are fermenting barley and other grains, we're making grain alcohol or perhaps beer, depending on the type of brew that we're doing, whether or not we distill it at the end or not, etc. So ethanol, one of the more widely consumed beverages in the world, of course. Methanol, also known as wood alcohol, is another common product that finds use in a variety of things. Methanol, it turns out, is actually used in a number of windshield washer fluids to keep them from freezing. It's a mild antifreezing agent that you can add to these things. It is quite toxic. If you ingest as little as 15 milliliters of this, it can cause you to go blind. 100 milliliters can cause death. And it's because methanol gets processed in the liver to formaldehyde, and as my biology friends will remember, formaldehyde is that molecule that you all use to preserve tissues and specimens. So if you've ever worked in a biology lab where you're preserving things like frogs and worms and fetal pigs and that kind of stuff, they're quite frequently packed in a solution of formalin, which is really nothing more than formaldehyde and water. And so anytime you preserve a tissue, you're actually killing it. So that's why methanol can cause deaths. 2-propanol, this is the alcohol that you get when you go to a CVS or Walmart and buy some rubbing alcohol for use in the home. It's a very mild antibacterial and is used to treat small cuts, scrapes. Some people use it to remove or to help unclog pores because it will also dissolve greases and things of that nature. And it evaporates fairly ready and produces that cooling sensation that you might use after a workout to cool down your muscles a little bit. Ethylene glycol there at the bottom, that is the major component in the old-fashioned antifreeze. And I say old-fashioned now, hasn't been that long ago, but automobiles nowadays really don't come with ethylene glycol as the antifreeze component in it because ethylene glycol, it turns out, is actually quite toxic. If you were to, in the old days, a lot of people would change their antifreeze every few years, and if you happen to leave that out lying around, animals would come along and drink it because it is extraordinarily sweet but toxic. And so nowadays we use a different we use propylene glycol, I believe, is the major component in most antifreezes today, which is not toxic like ethylene glycol is. And ethylene glycol gets processed in the liver very similarly to ethanol and methanol, but the byproducts of that process are quite toxic. There are some interesting ethers. These are known as the crown ethers. You can see why they're called a crown. If you were to build a model of this with your model kit, you would see that it zigzags around where the oxygens actually occupy kind of the tips of a crown, a royal crown, if you will. The nice thing about these is we can control their size. So there's an 18 crown 6. It gets its name because there's 18 atoms in the in the crown ether itself, 6 of which are oxygen. And you can control the size of this pore, and you can also have 12 crown 4. Notice that the pore size is actually smaller. And we can tune these so that they can complex different metal cations. So 18 crown 6 is really good for complexing with potassium ions, whereas 12 crown 4 is very useful for complexing with lithium. And this type of process can actually be used to separate lithium from potassium salts fairly selectively in a process known as molecular recognition. There are a few interesting epoxides. Epoxides are ethers, but they're a special class of ethers. They are more reactive. You'll recall that they're more reactive because the oxygen atom is actually part of a 3-membered ring, which has substantial ring strain associated with it. And so we find that epoxides will actually undergo chemistry that typical ethers just don't undergo. So for example, if you look at Parapolone B, that's the cockroach sex pheromone. There was a lot of work at one time done on making that because it has 1, 2, 3, 4 chiral centers plus a stereo isomer possibilities there at the 1 alkene that's shown in the trans position, or trans configuration, excuse me. This was a very important project because if you're in pest control, if you want to try to catch cockroaches into the little cockroach motels, they bake them with the sex pheromones so that they can trick the cockroaches into thinking that there are females ready to mate, and they walk in but never come out. Epithiolone B, that's an anti-cancer drug. You can see there that it also has an epoxide functional group within it, and it's necessary for it to function in its anti-cancer mode of actions. We can prepare alcohols, ethers, and epoxides using a variety of different chemistries. You can prepare ethers and alcohols using SN2 chemistry fairly readily. So for example, if you take an alkyl halide, primary alkyl halide that is, and react it with sodium or potassium hydroxide, you can get an SN2 reaction to occur where you get an alcohol. You can replace the OH, or the hydroxide, nucleophile with an alkoxide, and you can essentially use the same type of chemistry to make, instead of alcohols, ethers, which can either be symmetrical or unsymmetrical, depending on the number of carbon atoms that you have in the starting materials. If we make ethers this way, this is known as the Williamson ether synthesis, and this is something that you really need to commit to memory in terms of a name. There are several name reactions this semester that you're going to need to know by heart, so commit the Williamson ether synthesis to memory. In terms of formation of alcohols, you'll recall back from 255, this is really review here, that we can form alcohols by hydration of alkenes under an acid-catalyzed hydration. This works really well for alkenes that can give tertiary carbocations. The carbocation that's formed then reacts with the water to give a protonated alcohol or an oxonium ion, which then undergoes deprotonation to give the final alcohol product and regenerate the acid catalyst. We talked about that an awful lot in 255. You need to go back and refresh your memory on this mechanism and have it committed to heart, really. Don't forget, though, that under these acid-catalyzed hydrations of alkenes, we can have carbocation rearrangements. So anytime we generate a carbocation, don't forget that cardinal rule of carbocations that I've shared with you before. So go over that in your notes from last semester. But basically, remember that if we form a carbocation, if it can rearrange to a more stable one, it will. And so we've always got to be mindful when we're generating carbocations. So in this particular case, we generate a secondary carbocation, and that should be a dead ringer for a stop, pause, and think kind of event, because we know secondary can be formed, but they're not the most stable. So always look for the possibility of rearrangement. And in this particular case, we can get a alkyl shift or a methyl group shifting over to the secondary carbocation to give the tertiary carbocation, which then undergoes addition of water and deprotonation to give the alcohol that results from carbocation rearrangement. Well, we're not dead in the water because we can actually use oxymercuration, demercuration to avoid rearrangement. So you might recall in the first step, oxymercuration makes the OH bond to the alkene and the organometallic oxymercuration product, which then undergoes demercuration by the addition of sodium borohydride and water to give mercury metal that falls out of solution. This is exactly what we did in that demonstration that I did last semester. So you can go back and think about that particular demonstration and how that worked as an example. The nice thing about this is that it avoids rearrangement because you never have a true carbocation intermediate, right? So let's look at some examples. 1-hexene under the oxymercuration demercuration sequence, we can get 2-hexanol. That should be hexanol, not hexenol. 96% yield. 1-methylcyclopentene will undergo this reaction to give 1-methylcyclopentanol. Again, very good yield, Markovnikov products. And now our 3,3-dimethyl-1-butene, which if we're just doing acid-catalyzed hydration would undergo a carbocation rearrangement, we find that in fact no rearrangement occurs here. We get 94% yield of this particular product. We clearly get the secondary alcohol. All the methyl groups are attached to the carbon atom that they were attached to in the starting material, so obviously no rearrangement occurs. And the reason is because we don't have a carbocation that gets formed during this reaction. It actually goes through the mercurinium ion species that you see here. So it's the mercury atom that actually bears the formal positive charge. And then water will always attack these mercurinium ions at the carbon atom that is the most substituted because that carbon-mercury bond actually is the weakest of the two carbon-mercury bonds present. Okay? And so you end up with the anti-product where the mercury and the OH are actually going to be on opposite sides of that ring. So that's an anti-addition, if you will. And then once we reduce off the mercury with sodium borohydride, we end up with the Markovnikov alcohol. We know that alcohols can act as bases in nucleophiles. Alcohols will react with strong acids, and you can end up getting a protonated oxonium ion. And this chemistry then can undergo a variety of SN2 reactions where a nucleophile can displace the protonated alcohol as a leaving group, and that leaving group happens to be water. Now this slide is where we actually picked up with in Friday in class, and so I'm going to stop the lecture at this particular stage. See you all next week.